record. Sorry, anybody listening to the recording. You jumped in the middle because I forgot to push record. So here we go. All right. Let me give you an example of this alternating series. Here's one. If you have the harmonic series, right, 1 over n, it's a pretty ugly 1 over n. If you have 1 over n, we already know that this series diverges. But what if we were considering this series, n equals 1 to infinity of minus 1 to the n over n? So this one's alternating, right? It goes up and down and up and down and up and down and up and down. Well, guess what this one goes to? This one goes to 0. Okay, so when we made it positive, we ended up with a series that diverged. So there are some very special series, alternating series, okay, that fall into this category. And if they do, then we use what we call the alternating series test. And we say, if the terms are going to 0, okay, and they're decreasing, then we actually say that it converges conditionally, okay? And again, the vocab and the language here, not that important. I just want you to see kind of how we would think our way through this. All right, so given that we haven't decided yet, we're gonna then try the integral test. And we're gonna talk about the integral test today. So we're gonna learn that one. If the integral test can't be done, then we're going to do the direct comparison test. And I was talking about the direct comparison test a little bit earlier. So it turns out that we have sort of a whole bag of tricks, if you will, a whole bunch of different tests that we can use to decide where a series is going. And we've only looked at a few of them, but I hope that you've kind of got a flavor of how this works, right? A taste of how this works, a little introduction. And if we have more time, then we would investigate more series. I made a decision, and I usually do this time of year anyway, that we could just keep doing this all the way to the end because there's enough material. But what I'd rather do is pause here and see what we might use the convergence of series for. Like look at an application. When are we ever going to use this? Before we dig deeper into learning if it converges or not and learning a bunch of tricks for it, I want to go off and say, when would we ever use this? So that you have a feel for that before we give it up, okay? And then if you have run across sometime a series that's maybe more complicated than the ones we had a chance to look at, then you could go back and learn some more tricks, some more techniques for deciding convergence, right? And I think you'd already have a good start on that and then be able to investigate it some more in a class down the road. Okay, so that's where we are. I will send you the big spreadsheet form in case you're interested. And what I want to do today is I want to, I'm gonna switch, okay, here we go. I want to investigate these two series in a little bit more detail. Okay, because these seem to be really good ones. If you know these two, then you can get a lot of other ones based on these, right? So if you know these two, and of course we already know this one, the sum n equals 1 to infinity of a r to the n minus 1, right? We know geometric ones. So we've got this one, they're geometric. We've talked a little bit about alternating. We're going to make it positive. That turns it into this kind. And then I want to talk about these two. So let's start with number 1. And I think we've already seen this in Desmos, but that's always the first thing I would do. So let me jump over and share that with you real quick. Desmos. All right, so I would already put a bunch of these in here. In fact, this is kind of a nice thing to even look at. I was kind of playing with this. Check this out. Here's my sum of my red series. Okay, this is series A, 1 over n. This is 1 over n. What's it doing? It's not bending fast enough. It's going off to infinity. So what if we had a different series whose terms were always bigger? Well, if this is running off to infinity, it's going to force this off to infinity as well. Do you see that? That's the comparison test that I was talking about earlier. And I was going to talk about that a little bit more today, but I don't know if I am. All right, so I'm getting rid of B. and I'm keeping the sum of the a's. Notice I've got a sub I in here correctly today. All right, and so I'm getting rid of that. And here are the sums. So I'm going to put the sums up there. And here's my series. So green are the terms, and red are the sums. And I'll get rid of that. And then let's look at n squared first. So we're going to look at n squared. So here go the terms, right? Terms are getting smaller, smaller, smaller. And the sum looks like it's getting bigger, 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 bigger. In fact, it looks like it's kind of leveling off here. So based on Desmos, I'm going to guess that this actually has a limit and that it converges. Everybody good so far? Okay. I want to show you one other tool that normally I might not let you use, at least not at first. But I think that maybe you should use it, and you should definitely know that it's there. So there's a website called Symbolab. I know we've been to it before. And I think it's a kind of a cool one, because in Symbolab, you can ask it to do integrals, which I think you've used it to check integrals before. But you can also do the same thing for finding out what a series is doing. So if we want to know what 1 over n squared is doing, we might just ask Symbolab to tell us. And Symbolab is going to say, hey, check it out. The sum n equals 1 to infinity of 1 over n squared converges. Beautiful. So at least you know what the answer is. Right? And it would still be nice to know, how did Symbolab decide this? Right? Did it just graph like Desmos did and guess? Or did it do something a little bit more sophisticated than that? So this is good news, because you've got Desmos now. You can look at it. You can say it looks like it converges. Then you can go to Symbolab and you can type it in, and you can have Symbolab tell you, yes, in fact, it does converge. And it tells you which test to use, or which test it used anyway, because sometimes you can use different, just like integration techniques, sometimes there are different tests that'll work on different, multiple ones. But it used the p-series test. So at this point, you either know what a p-series test is or you don't. And we kind of don't. We kind of do a little, but not really maybe that great yet. And then I got some good news and bad news. Right over here on the show the steps, that's about the time you're locked out. So if you can afford 99 cents a week or $12 a year, then you can get it to give you a little bit more info. So I've had students before do this, sign up. And I've had other students use other websites. I kind of actually really like this one, and and for the most part, I don't try to convince you to pay for something, and I wouldn't try to convince you to pay for this. I mean, we're only going to be on it for like 3 more days. So if you want to pay $1 for a week, you can look at it for a week or two. But if you were going to take a whole course, maybe another year of mathematics, and it was going to involve a lot of sequence and series, and maybe a lot of integration, then I might recommend that this is a pretty good website. It would be a pretty good $12 spent, right, for a whole year. And so I happen to be a member, so let me just click on the show steps. And then it's going to give you some details. It's going to say if it's in this form and p is greater than 1, then it converges. So if we go 1 over n squared or 1 over n cubed or 4th, 5th, 6th, 7th, if p is between 0 and 1, then it diverges. Okay, so maybe we can prove this p-series test. That's what it's going to open to do today. And so it just gives you the actual test. Now, of course, you could have just quick turned to your book, looked in this section 11.3, and read, well, so use the p-series. What's the p-series? And then it would have given you the definition. Right? So it's kind of nice, because you could also click on here to practice some different ones. So if you wanted to try some more p-series tests, you could click on practice, and it would give you some problems. Like, what's this one do? Well, that's the one we just said. So it converges. So then you can check. right? And then you can say, hey, give me another one. How about 1 over n cubed? What do you think about that one? Boom. It converges. It's a p series, and p is bigger than 1. Are you with me? You're like, no, you're going too fast. Yeah, that's not a big surprise, okay? You'd need a few days to kind of dig in and practice on this, right? And so, these are all easy. To the 4th, converges, yeah? How about getting something harder? To the 5th, converges, okay? So you would keep, to the 1/3, now what? 1 over cube root n. Well, at this point, you might say, I don't know. And you'd come back here and you'd say, well, what if it's n to the 1/3 power? Then what does it look like on Desmos? That's not looking too good, is it? There go the dots. I'm kind of thinking, well, maybe if I zoomed way out, it would start bending. Yep, it starts to bend. But is it going to bend enough that it ever levels out? And the answer is no. Okay, and so if we go back to Symbol Lab, we'd say, I think that diverges. Let's check. Yep, you're right. So now we've gotten to the point where we can look at a p-series and we can say, what we think it's doing, but we still haven't made a proof yet. We didn't prove this is true yet for all p's, and that's kind of what we're up to next. Okay, so I really like Symbol Lab for testing series. You can do this to not as great of an extent using your graphing calculator. Your graphing calculator will tell you if a series converges or diverges. And if you want to see kind of the steps on the TI-89 and you've never done that before, you can ask me later and we'll kind of go through the steps. Or you can look online and say series convergence TI-89, and you'll get a whole bunch of information about how you can test series using your calculator. Okay, so what happens? Well, what happens is you're going to need to know if a series converges or diverges, and you're going to need a tool for deciding that. And so this seems like a pretty good way to do that. If you're going to be real serious about math and go on down the road, then you're going to have to get to the point where you prove these things. And of course, we're going to need a little bit more time for some of the proof. And you can study that in maybe your next math class if this seems interesting to you. Okay, so what if I did want to do something a little stronger than it looks like it or Symbol Lab told me, right? That's what's next. So let me show you something called the integral test. And of course, the integral test is a nice one because we happen to be experts at integrals, right? And so anything involving integrals ought to be a good test for us to use. That's why I like to start with this one. So here's the first thing. We've got a series, all right, 1 over n squared, that's defined for the values of the positive integers, right? We're putting natural numbers in here. So all we have are dots. But I'm thinking that the values in our sequence are actually following along the function y over 1 over x squared for all real numbers. So this particular test is only going to work if our series is following some nice real valued continuous function. We want to do an integral, right? Integrals only work nice for continuous functions because only continuous functions are differentiable and so therefore anti-differentiable. So the first thing that you would have to check, let's see if I can get back over here, is my series now, right? Is my series 1 over, this was the squared, right? Whoops. 1 over n squared. Is my series, right, the green dots, is it following my function f of x equals 1 over x, right? Squared. And it looks like, yeah, you know what? The green dots are following right along the function. So we already learned that wherever the function goes, then the green dots have to go. Right? This was really handy for finding the limit of a sequence. And it's going to be handy for doing this test as well. Okay. So it shouldn't be too hard then for us. Oh, I started at 2 for some crazy reason. It shouldn't be too, I'm going to turn those off for a second. It shouldn't be too hard for us to find the area under the curve 1 over x squared from 1 out to infinity. Consider that area for a minute. Here, I'll draw a picture of it over here. Consider the area under the curve, right? F of x is 1 over x squared from 1, right, to infinity. Find this area. You say, oh yeah, I'm good at that. That's an improper integral, right? That would be the integral from 1 to infinity of 1 over x squared dx. Yeah, making sense? Good review for the final now. This is stuff you should be able to do, integrals, right? Even ones with infinity for limits. So we write the limit as t goes to infinity of the integral 1 to t of 1 over x squared dx. And then we find what that is. So let's see, if it's x squared now, I think we can anti-differentiate using the power rule. So we would get the limit as t goes to infinity. What is that? Minus 1 over x. Yes?
Yeah.
You can change it to a power if you want x to the minus 2. It's the minus 2 now. Must have been the minus 1 before. I need a minus 1 to take care of the minus 1. Okay, so I got minus x to the minus 1, which is minus 1 over x. Or you could just memorize that one. Right? Memorizing it was faster. So now we got to plug in the limits of integration. So here they go. Put in t. We get minus 1 over t minus what we get when we put in 1. So that's minus a minus 1, so plus 1. And then we find this limit. So tell me about this 1 over t. Where's that going when t gets big?
0.
0, meaning this goes to 1. So this area in here, right? This area is equal to 1. Everybody happy so far? Okay, so let me put my dots of my series on here. So what are they? They're 1, 1/2, 1/3, 1, oops, I'm on the wrong one. I'll go back and do this one next. We were doing the squares, weren't we? So 1, 1/4, 1/9, 1/16, 1/25. We good? Ready? Now check this out. This is super cool. See if I can figure out how to do it. Check out this, I always get this backwards. Let's see. Maybe we do it this way. Maybe we do it this way. This way looks good. Okay, check out that little rectangle right there. How big is it? Right? How much area is there? Well, this distance is 1, right? And this height is what? 1/4.
Yeah.
So it's 1 by 1/4. So the area in here is 1/4. Okay, now check out this rectangle right here. Since I'm going one integer at a time, right? My delta x is 1. So my width is still 1, isn't it? This is 1 wide. And how tall is it?
1/9.
1/9. So this would be 1/9 of area. And then this one would be 1/16 of area. And then this one would be, they're getting kind of small here real fast because they're squares. This one would be 1/25 of area. and then it would keep going. We agree?
Nope.
Okay, so what if I add up all these rectangles? I would get 1 plus a ninth. Nope. I would get 1/4 plus a ninth plus a 16th, right? Plus a 25th, and I would keep going. So what if I added all these up? I'm going to argue that if I added all these up, that my area of all these rectangles would be less. It would be less than the area under the curve. Do you agree? I mean, all the rectangles are under the curve. There's a little bit hanging over right here. I don't know how much it is, but for sure the area under the curve is more than the area of adding up all these rectangles. So if I add up all these rectangles, I got to get a number, don't I? I mean, it has to go to a number. Maybe I should call it S for sum. Which means it has to converge. And then if I add a 1 to it, well, if this converges and I add 1 more, then that also converges. Do we agree? Huh. What does that mean? It means if this integral, if this area goes to a number, then this sequence has to converge. Now, I don't know what it converges to because I don't know how much area is left over, right? I don't know what this sum adds up to. I know it's going to add up to a number that's smaller than 1 because this area is 1. Are you with me? Well, I'm sorry. This part right here has to be less than 1. And so then I would add this 1 to it. And so this big sum right here has to be less than 2. Okay, I don't know what number it is, but I know it has a number and I know it's less than 2. Well, it turns out that it does have a limit. I mean, we just proved that it has a limit. We proved that it converges. Figuring out what it converges to turns out to be harder. Yeah, it turns out to be a lot harder. Now, one way we could estimate what it converges to is just add up a whole bunch of terms. I mean, Desmos is actually quite good at that. We could just say, add up the first 1,000,000 terms. I don't know if it'll do 1,000,000, right? But we could say, find the sum. I called it series A, okay, of the first 100 terms. And what do we get? 0.6349 or so. That's good. Some number, right? That's less than 2. Did I get everything right? Oops. This is starting at 2. This needs to start at 1. Should be bigger. That looks better, doesn't it? It's more than the first rectangle, which was 1. And it's less than the area under the curve, which was 1. So 1 plus the 1 less than 2, we're in good shape. So what if I added up more of them? You know, more. It looks to me like this is getting closer and closer to about 1.644344057. I don't recognize that number. It's not square root 2, and it's not pi, and it's not e. You know, and but it might be this. It might be pi squared over 6. It might be pi squared over 6. Why didn't it compute that? What the heck?
I think you have too much going on. I've noticed that.
What's that? This is too big? There.
No, I mean like with all the other summations and things like that going on.
It can't figure it out. That's interesting, isn't it?
Yeah.
I didn't know that it did that. Let's clean up just a little bit then. I don't know what's happening. Should be able to compute that. Let's say, I don't know, S.
Yeah,
equals.
that's what it is.
Is that what it is? Did it work on yours? I don't know why it's freaking
Did it on
out.
the touch? It's 1.6.
Yeah, I got the same.
93407.
Okay. I don't know why mine's freaking out, but whatever it is. Okay. this is going to be a mystery. Sorry. I mean, I solved some of the mysteries of your life, right, in this class. We did them together. Like, remember back in 3rd grade when someone said the area of a circle with radius 1 is pi? And you just had to take that on faith until, well, this year. So most of your life, you had to take that on faith, that the area of a circle is pi r squared. And this year, we actually proved it. Well, unfortunately, I'm going to leave you with the sum of this series is pi squared over 6. And you're going to have to take it on faith until we prove it somewhere down the road. At this point, I don't care. I don't care what the sum is. I just care that it actually has one. So we wanted to prove that it converged. And this trick that we used is a great trick. It works when, doesn't work all the time, but it certainly works for a lot of them. And when it works the best is when the terms of our sequence follow this real valued function. And so if these terms are following this real valued function, we can use the integral to get the area. And then we can say the area of our sum is smaller. And since this goes to a number, the area of the sum has to go to a number, which is beautiful. And we get convergence. So here's some drawbacks. First of all, there are some functions that don't follow a real valued equivalent. And the big problem with those, we've already seen a few of those. What if I gave you a sequence like this? A sub n is n factorial over n to the n. Okay. Then in the factorial function, you can't put in all real numbers because we don't know what 1/2 factorial means. Okay, so this test wouldn't work for this series. There are some other ones that are bad too. Look at what we do in the integral test. What we have to do is we have to find, right? We have to find this integral. So what happens if this function is really, really messy and techniques from chapter 7 won't get it done? Then yes, it would be true if we could find the area that the series would converge. But what if we can't find the area because we don't know how to do the integral? Then this test won't work so well. Okay, now fortunately for us, we have a bunch of techniques for solving integrals, and the ones that you'll see in the homework are all doable. But in general, this could be really messy, and we might not be able to figure this out, which means we might not be able to use this test. Okay. This test works great the other way too. Let me do it one more time for you. All right, let's do this one. The sum n equals 1 to infinity of 1 over n. Did you see that cool proof that I did? It was like kind of messy. It was really hard to follow. I basically said these terms, okay, when I add them up, are going to be smaller, or sorry, are going to be bigger than the terms of a different series when I add them up. A series that I can actually figure out where it's going. I use the comparison test in my proof. Right? So it's kind of a slick proof, although it seems a little quirky and like a trick almost. But now that we have the integral test, hey, let's try that instead. Maybe this test will work better. So what I'm looking at is the function now, f of x equals 1 over x. And so there has to be a function. And of course, my terms have to be following along this function. Okay, and that's certainly true for 1 over n and 1 over x. So it seems like then that if I did something similar, okay, only this time I want to put my rectangles over the top. Okay, so I'm going to build left-edged rectangles. Oops, sorry about the focus. I'm going to use left-edge rectangles now and put them over the top. So what's this? This is 1, 1. So this is 1 tall and it's 1 wide. Sorry about the distortion there in the drawing. So this has an area of 1. And so where am I here? I'm at 1/2, yes? I'm at 1/2 right here. Yeah. So it's 1/2 tall and it's 1 wide. So it's the area is 1/2. So now when I put in 3, I get 1/3 tall, and it's 1 wide. So this area is 1/3. So if I add up all these rectangles, I get 1 plus a half plus a third plus a fourth plus dot, 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 and it keeps on going. Everybody happy so far? This is kind of review. This is a big review. That's why I like ending with this stuff, because we did this years ago. Some of you did it twice, right? Because you did it at the end of Calc 1, and then we definitely did it again at the beginning of Calc 2. If I add up all these rectangles, though, it looks to me like they're hanging over the curve. They're always above the curve, aren't they? So this would be an overestimate. So whatever the area under the curve is, the area of the rectangles is going to have to be bigger. Everybody agree? In a graduate level class, you would have to prove that's true for all continuous functions, right, that meet these criteria. You'd actually have to prove that's true, but it seems pretty obvious. We're going to leave that for now. All right, so let's figure out what the area under the curve is. That's the area from 1 to infinity of 1 over x dx. All right, so what's that? Well, we write the limit as t goes to infinity of the integral 1 to t of 1 over x dx, and then we try to find this integral. Do you remember how to find it? You say?
You can bring x up to the numerator and just use power rule.
You could, but think about it. If you brought it up to the numerator, you'd have x to the -1. So it must have been 1 bigger. That would have been x to the 0, yeah? X to the 0 is going to be a problem because that means it would be 1 and its derivative would be 0. Oh, no, this is a problem. Try again.
So you could just do ln x.
You absolutely could, right? We had that one memorized, didn't we? That's the natural log. Do you remember how we proved it was natural log? I think we took the derivative.
Parts?
Oh, with parts. Oh, parts. No, I don't think so the
Was
first
it-
times.
Don't think part was parts. No, I don't think parts is how we proved that it was natural law.
This was the problem that we were working on. Do you remember? How do we prove that? What if we did this first?
You have to rewrite it as e to the.
Yes. We did the natural log in terms of the natural exponentiation function, right? We rewrote it with an e in there. That was the trick. Okay, here we go. You've got it memorized. Natural log x from 1 to t. All right, let's put them in and find out where this thing goes now. So we've got the limit, t goes to infinity. This is the natural log of t minus the natural log of 1. Natural log of 1 is 0, isn't it? Okay, well, where does log t go when t goes to infinity?
It goes to infinity.
It sure does. So probably in your head, you should probably have maybe this graph, yeah? The natural log graph in your head, so that you can kind of think about where it's going. This goes to infinity. That right there is where it crosses at 0, at 1, 0. This goes to infinity. Uh-oh, this goes to infinity. That means that the area under this curve is infinite. Well, what does that mean about the area when I add up all these rectangles?
Infinite.
It's got to be infinite because the area of all the rectangles is more than the area under the curve. And the area of the curve is getting bigger and bigger and bigger without bound. So that means the area of the rectangles has to be getting bigger and bigger and bigger without bound. So what did we prove? The harmonic series diverges. This is a name, right? We call it harmonic series. Any of you know any applications from other classes where we use the word harmonic?
far as I know, that only shows up in like musical related things.
Yeah,
Yeah,
I was like, I know that from like a music term.
it's definitely a music term. And maybe I can remember where that's going to show up for you. It's going to show up in some places in physics, I think. And
Yeah,
definitely,
I was gonna say the places that I remember is using it. Well, not really using it, but a term representing like resonance frequencies and stuff like that. Like things have a natural harmonic, so there are certain frequencies where weird stuff can start to happen. So I think that's probably where it shows up in physics.
that's exactly right.
Oh yeah, like the shattering wine glass.
Yeah, exactly.
That's right.
Yeah.
Shatter, in fact, that's a pretty good example. So I'm going to reach here a little bit. You can fact check me later, right? But I'm kind of thinking that if you were adding up vibrations and they were getting bigger and bigger and bigger and bigger, then maybe the Tacoma Narrows Bridge would fall down, or maybe the wine glass would actually shatter. That sounds like diverging to me, getting bigger and bigger and bigger. Okay. Now, don't get me wrong. I think that's an oversimplification of what's happening, but certainly there's something going on there that you could investigate a little further down the road. Okay. I find that the hardest thing about sequence and series when you first get introduced to them is that we spend all this time just looking at these series saying, well, what's it doing? Is it getting bigger, getting smaller? Where's it going? But we never really get an opportunity to stop and say, well, when am I ever going to see one of these in real life? Right? I mean, we did see a geometric series with the dosage problem, right, in the homework. So you can go explore that one a little bit. But we only have so much time. So I'm going to have to give you a little delayed gratification here, but it's always fun. One of my favorite things was I'd be sitting in my music theory class or my physics class on sound and light. Okay, and then bam, the stuff would just come back up and it'd be like, this is blah, 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 blah. And they'd always say it like, probably most of you don't know this because none of you have had enough calculus. And you'd be sitting there going, wow, wait, I understand that. And that's kind of a fun thing as you go down the road. So maybe that will happen to you as you get further along. And it doesn't just have to be physics, right? The application of accumulating a dosage, you might see in nursing, or compound interest, you might see in finance. So I think there are a lot of places where this is going to show up. And I think that'll be kind of fun for you as you see it down the road. Okay, we call this thing the integral test because we compare the sum of the series to the area under a curve, which we find using the integral. Can't always be done because we can't always represent the series with a continuous function. And sometimes we can't figure out what the integral is. So we can't finish off the test. But for P series, it works great. And in the end, what we end up with is the sum, n equals 1 to infinity, of 1 over n to the p. And we can classify all of these. If p is greater than 1, converges. Right? If p is between 0 and 1, diverges. If p is negative, then what happens? Then the n goes up to the top. You with me? So if it was like -2, it would go up to the top and we'd have n squared. Well, if I add up a bunch of squares, it's definitely going to diverge. Yeah. So the p series that we're concerned about is if p is bigger than 1 and it's down there in the bottom, bam, we got it. This is going to be sort of the second group of series that you should be familiar with. The first being geometric, and now P series being the second big group. That takes care of most of the ones that you're going to see out there in the world. But certainly it doesn't even scratch the surface of all the possible series that are out there. We certainly saw some telescoping series. We saw some with factorials in them. And they're just like, well, it's pretty much anything in the universe that you want to write right there. Okay, and then we say, well, what happens? I don't know what happens, right? You can write anything in the universe there and then go explore it. And so as you get more series that you need to investigate, then you might have to dig a little deeper and find some more tools. Okay, but I think that we've got an idea about how this thing's going to work. Okay, basically, we should go through the following steps. Let me see if I can recap, and then we'll see if we can shut this thing down for today. Here is a whole page that from year to year, I'm, maybe a little further or a little less far, and, we do some of these, right? But when you could comfortably do all 38 of these, then I would say that you, that you know more than most calculus students. Okay, so what is it? They're just all mixed up, all different kinds, all mixed up. So what do you use? The flow chart, go through the flow chart. But you really didn't get the full, month-long experience of learning all those techniques. So what would you do, right? You would have to maybe pick one. So let's pick one. How about number 4? I don't know. Look okay? Boy, I don't know. Number 2 looks a lot easier to me. 2, I'm feeling like the bottom's getting bigger faster than the top. Do you see that? A lot faster. And so what's happening with number 2? I'm pretty sure those terms are going to 0, and they're going to 0 fast enough that this is going to converge.
Yeah.
Okay, but what about number 4? Now I've got n squareds over n squareds. Uh-oh. And they're alternating back and forth. So maybe I don't know what this is doing right off the bat. I know that maybe the first trick that we would do is make them all positive. So take the absolute value and look at where the absolute value of the series is going. But what you should do, if you run across one of these out there in the world, and you're not in a graduate math class where you actually have to prove it, you just jump out like this and do the same basic stuff that we've been doing. You're going to go to Desmos and you're going to put it in here and you're going to say, what was it? It was -1 to the n. Ooh, which one was it? -1 to the n. Good grief. My thing's not being too happy here. -1 to the n. On the top, we had n squared -1. In the bottom, we had n squared plus 1. That looks right. I don't know why it wants these. Oh, it doesn't need those actually. Right? You might want maybe parentheses right here just to make this a little bit more readable. Right? You might want them right there. Okay, so what do? You put it in there and you say, this is my sequence now. So where is it? Where is it? That's a good
Yeah, I
question.
think it's turned off actually.
It's turned off. It's supposed to be blue. I got some problems. I think I blew up this whole Desmos. I mean, I think it's like kind of blown up. So you might want to, do this. I'm going to copy this, copy. And then maybe at some point you say, start a new graph, start a new, where is that? Start a new blank graph. So if it gets completely confused, start over, yeah? So what do we got? We got a of n, a sub n, right, is equal to, and then here's our formula. Okay, whoa, look at them, they're teeny tiny. How come? Because we didn't put the dots in. So we want to put in just the integers now. Because -1, right, to the fraction power sounds bad to me. So we say our list is going to be 1 to maybe 100. I'll try not to blow it up this time. And then we're going to say graph n, a of n, and just give me the dots. So what are the dots doing? Boing, 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 right? And each set of dots seems to be getting closer to 1 and -1. So the next thing that we would do is we would maybe say, I don't know, b sub n, right, is the absolute value, absolute value of the a sub n's. good grief if I can type. I thought it was just the classroom, but it seems to be everywhere. Okay, and then maybe we would look at the bees. So what are the bees doing? Look at the bees. They're all going to 1, aren't they? So then you'd say, all right, well, that's all fine and dandy. What's the sum doing? So you'd say the sum, the nth partial sum. It's the sum. You got to remember right here to make this an I. I always kind of forget about half the time. So you'd say 1 to n, and we're going to add up the a sub n's. Okay, so where's the sum? Where is the sum? Right? Let me graph my bouncing terms again. There's the bouncing terms. Where's the sum? I usually make it red, so I'll make it red. I don't even see it. You say, well, that's because it doesn't work unless you just do the dots. So graph n and the nth partial sum. There they are. There they go. What do you think? Sure looks like diverging to me, doesn't it? I'm going to call that diverging, bouncing further and further and further apart. So is this enough? Well, no, this is a good start, right? You can figure out what, do I have a typo? What's up, Katie?
It should be a of I.
A of I, you got to get this right. And so you're following me along pretty good. And so we don't want to graph that. We want to graph the sums. So now look at the sum. Oops, that's the red ones. So maybe I'll turn these off. There's the sums. And then you say, I want some more of them. So I'll go out to the first 100 maybe. What just happened there? 100. There's 100 sums. Does that look like it's going to a number?
Yeah.
It does? What number?
Well, I'm not sure then.
I'm thinking that if we were to look at these way out here, that it's going to bounce. This is bouncing back and forth between two numbers. You see that? So it's not going to an actual number. It's actually just bouncing. So we would say this sum just oscillates, right? Somewhere between, I don't know, 0.8. What is that? About 0.8 maybe? 3/4 maybe? And about 1/4. So it bounces back and forth between 3/4 and 1/4. You seeing that?
Yeah.
Now, the good news for me is I made a typo and I would have got it right anyway. I would have said it diverged. This one also diverges, eh? Sometimes you get lucky with your typos. Okay, but what I would hope that you guys can do after studying this section is that you can understand what's happening with the series and the sum, and that you can use Desmos to investigate it. We're not going to be the greatest at proving this is true, but we're going to have an idea how we might go about doing that. But I'm not going to hold you accountable to the proof. It would be nice, though, if you could kind of investigate it a little bit. One other thing that we might do before we leave, I don't know, I probably have to type it again, is we could go in here and we could say, well, I wonder what Symbol Lab is going to tell me. I wonder if Symbol Lab's going to tell me anything. Why is it freaking out? Oh, I'm in the quiz. So go back here and say, all right, do this for me now. Sum, and I'm just going to kind of grab one so I don't have to type it all. And then I'm going to say, I'm going to try to get in there and say, whoops, didn't like that. I'm going to try to get right there. And I'm going to try to say -1 to the nth power and put a parenthesis around this fraction. I guess it doesn't need one. The top was n squared -1, and the bottom was n squared +1. I think that's right. And I'm going to say, where is this going? and it's going to say it diverges. And so for free, right, for the free version, it's going to tell you it diverges. But for you to see the steps, right, it's going to even tell you, apply the divergence test. Right? What is the divergence test? Do you remember? The terms have to be going to where?
0.
The terms have to be going to 0. Well, where are these terms going? We got the limit as n goes to infinity. Is this on the page? Okay, there we go. Of -1 to the n of n squared minus 1 over n squared plus 1. When we take the absolute value, this turns into a 1, right? Focus. So how do I find this limit? Uh-oh, review time. Somebody say divide by the highest power of the variable in the denominator. So what do I get? I get 1 minus 1 over n squared over 1 plus 1 over n squared. Now, where's this 1 over n squared going? 0. And this one's going to 0. This is going to 1 over 1, which is 1. Where are my terms going? My terms are going to 1. Well, what if I add up infinitely many 1s? That's bad news.
Bigger.
It's getting bigger, it diverges. That's called the divergence test. In our book, we called it the simple divergence test. And of course, if you pay 99 cents, then it'll actually tell you what the divergence test is in detail. If the terms aren't going to 0, then it diverges. But of course, you could just look that up in your book. So I think Symbolab for free is still giving you a lot of information. Is that making sense? Excellent. What I would say is if we spend a month on this, then I'd expect you to be able to do some of these without help, without your book, maybe. I'd probably still let you have your calculator and Desmos, without your neighbors, okay? We haven't spent a lot of time on this. And so I think it's reasonable that you should get more resources, right, to be able to answer some of these questions at this point. And so what I would like for you to do is try a few of these questions. Okay, I gave you a few on a little quiz. You can use any tools that you want. You can use Symbolab. You can use I pay 99 cents and get the extra stuff if you want. You can use your book. You can use your calculator. You can use your neighbors as long as you're not looking at the quiz, right? As long as the quiz paper itself is not out on the table between you. Which means if you are confused about a problem, you can put away your test and then you can Zoom with one of your classmates and you can say, hey, I was having trouble with ones that look kind of like this. Can we talk about one of these? That's fair, okay? What I don't want is for you to copy somebody else's paper and turn it into me. So don't let somebody else copy your paper after you spent the time doing all the work, okay? Because that's not what I want to see. So try to do your own work, but do your own work using all of the tools that you have available to you. And I think that seems reasonable at this point. So there's a short quiz for you to do. It should be available now. I think it was available at 8:30 this morning. I think it's due, did I make it due Monday night? Just in case you had questions on Monday. Yeah, I think it's due on Monday night. So you'll be able to ask me some more questions about it on Monday if you're still stuck on a problem. Otherwise, in lieu of the homework from section 11, 4, 5, 6, 7, let's just do that little quiz instead. And then when you guys come back on Monday, I want to talk about power series and Taylor polynomials, which is like a super cool topic. So I think you're going to really like the last 2 weeks. Okay, any questions before we get going? All right, well, I'm sorry that went so long today, but there was a lot of good stuff there. And we did like 5 sections, so I'm feeling pretty good about that. But I'm going to let you go. Have a great weekend. Okay. And if you get stuck, if you're trying stuff on the weekend, you need some clarification or you're stuck, you can write me an email and I will check it from time to time and write you back.
Sure.
Okay.
All right.
Beautiful.
All right.
Have a great weekend and we'll see you on Monday.
You too. Thanks.